previously talked about this. We're going to pick up from where we left off. However, just for the interest of a review, I'll quickly go over the slides and then we'll move into the next slide. For your information, this module is module 35, as you would find in your My Canvas. Without further ado, let's get started. Okay. I'm just going to exit full screen here. Get this thing going. Hopefully we're still recording the screen. So, helicopter aerodynamic forces. Just like fixed-wing aircraft, helicopters also have similar four forces that we'll talk about. Like we did in fixed wing, we talked about lift, we talked about weight, we talked about thrust, and we talked about drag. However, as we discussed, helicopters do these and use these forces in a different way than your typical fixed wing airplane that feature a hung engine or power plant on the wing. Okay. Just like fixed wing, we have the same four forces of flight. Lift is right here, thrust, weight, and drag. For the helicopter, we have a combined vectoring with regards to the combination of lift and thrust. When the helicopter is in straight level flight, it has to separate some of the lift from the thrust and use the vertical component of the lift to support the weight while using the thrust to propel the helicopter in one direction or another. Lift is quite similar in fixed wing as it is in helicopters, as Bernoulli's principle still holds true. The airfoil has a specific shape. This allows air to move faster over the upper surface of the wing, which creates lower pressure on the top of the wing. For a helicopter, this would be referring to the helicopter's blade. So right here I have with me a blade for a helicopter, pardon me. And this blade, movement of airflow over the upper surface of this blade is what generates that differential pressure and creates lift. Like we discussed, helicopters primarily produce lift by rotating airfoils. Rotating airfoils is the primary principle of lift production. We also noted that the direction of airflow during powered flight is down through. So the propeller blades are pulling air from above the blades and sucking them down over the cabin and towards the surface or the ground. So this is normal powered flight. If the helicopter is moving forward, we have a tendency for the airflow to be sucked down through, and that's how lift is produced. Most of the lift produced, approximately 75%, is caused by that low pressure above the rotor disc. We know that because of the difference in velocity of the airflow from the root, or what I would call from the hub, to the tip of the blade, we know that the outermost part of the blade does not provide the same amount of lift as the more interior or the parts of the blades that are closer to the hub. So in order to equalize or account for this difference that we have in velocity, some blades are designed to have a twist, a washout. This will allow a lower angle of attack at the tip than what we have at the root. And another way a blade is designed to compensate for that difference is by using a thinner or smaller blade section at the tip. So the summary for this would be, because we at the very tip of the rotor blade, we're going to have very high velocity this will cause a tendency for us to create much more lift on the outermost portion of the disc, sometimes even risking overspeed. But by using some of these methods that we've just discussed now, you can potentially reduce by using a wing washout so that you have a lower angle of attack. You know that having a lower angle of attack would yield a lower lift production. Lift is the force that opposes weight. Weight is gravity's pull on a given mass. In this case, the mass is the helicopter itself. Lift must overcome at least the weight for the helicopter to sustain flight. The force of gravity opposes lift. When it comes to thrust on a helicopter, thrust is generated by rotating the main rotor system, which we have right here. Thrust opposes the force of drag. Drag is the force that opposes the movement of the helicopter. So once more, when the helicopter is in a hover, I know we discussed this earlier, the only type of drag that is experienced is, you thought it, you got it, only induced drag. Parasitic drag becomes involved or comes into play when the helicopter begins to transition from one point on a reference to the Earth's surface to another. And this also impacts our relative wind, as we discussed before. So in a hover, we have only induced drag because the thrust and the lift now combine to make one vector force, that basically the lift. The weight is pretty much constant unless you burn fuel, and there is no drag with regards to parasitic drag because the helicopter is stationary in a hover. Centrifugal forces are quite interesting when it comes to helicopter. The centrifugal force is the force that's trying to pluck the helicopter blades from the hub. So it's trying to pull it out as the blades rotate. And this is why when helicopters first spool up, the blades go from a drooped position and start to slowly but surely rise up relative to the plane of rotation. When rotor blades are at rest, they droop. So this is what we call drooping, when the tip kind of just sags below the plane of rotation relative to the hub, or in this case maybe the flapping hinge. As the rotors begins to turn, the blades rise from their static position due to centrifugal force. Huge amount of centrifugal force are exerted on the main rotor hub as the blades rotate. This is an example of what centrifugal force looks like. So centrifugal force is the force trying to pull this heavy mass away from this individual, while the centripetal force is the force that the individual is exerting on that ball to keep it under control. The helicopter's rotor head and blade grips provide the required centripetal force to counteract that centrifugal force. So it's basically an example of Newton's third law with regards to for every action there will be equal and opposite reaction. Basically that centripetal force is the force that is required to keep the system in equilibrium because of the centrifugal force that's trying to pluck the blades out. I'm not going to go too much into depth about Newton's first, second, and third law. You know that Newton's first law is reluctance to change the state of rest in uniform motion. You know that the second law simply relates the force that's required to move an object and how that relates to the mass of the object, and changing that force or changing the mass will determine how much the acceleration changes. Now, the interesting thing here to discuss next is with regards to torque. We talk a lot about main rotor torque. Main rotor torque is torque that is generated because of Newton's third law. The main rotor system is rotating in one direction. For example here, in the image we have here, the main rotor blades are rotating counterclockwise. So this will initiate a clockwise torque of the helicopter's cabin. So this includes where the landing gear, the cab, the whole system, and the tail rotor, everything wants to rotate. The tail boom, everything wants to rotate in a clockwise direction. So, and this is where we even talk about why we need a tail rotor. So the primary function of a tail rotor is to counteract main rotor torque, so that the helicopter doesn't have a tendency to just drift around as the helicopter's blade rotate in the opposite direction. However, because of this action that we're using our tail rotor to do, there is a tendency for the helicopter to drift. Now, this is a translation of drifting in the direction of the tail rotor's force. We should talk about the collective and how power can be adjusted in a helicopter's main rotor system. The collective lever movement positions the swash blades to change the pitch of the blade collectively. That's where the word collective becomes very obvious. As we raise the collective lever, this will cause all the blades to change their pitch at the same time. The key phrase there would be at the same time. And they would remain that way until they are changed. This causes the helicopter's blade or airfoil to produce a higher angle of attack, which will in turn lead to more lift as long as the critical angle of attack is not exceeded. To adjust power and the forward end of the collective lever, we have a twist grip or throttle, and this can help us to adjust the RPM. As the collective is raised, blade pitch angle is increased. As this happens, the angle of attack increases, but also so does the amount of drag. As lift and drag is increased, the speed of the main rotor slows down. So remember that as we have a higher angle of attack, while that is beneficial for creating lift, it's also simultaneously going to produce more drag, which would tend to slow the blades down. So effectively, to maintain RPM, we must either apply more power using the twist grip that's located on the collective lever, or we rely on a governor to do that from the engines, or a correlator to perform that function. A constant rotor RPM is maintained throughout all phases of flight. A power change is required anytime there's a change in drag. So in order to maintain that constant RPM, many helicopters use a correlator or a governor. Correlator is a mechanical collective to throttle linkage that increases engine power when the collective is raised and decreases engine power when the collective is lowered. A governor is an automatic engine power control that uses a sensing device to monitor rotor RPM and adjust the throttle accordingly. So this is a picture of the collective lever, and obviously this area is a twist grip, and you can twist that with your arm to adjust the amount of power that is produced. On a piston engine powered helicopter, power is measured on the engine's manifold pressure. On a turbine powered helicopter, power is indicated on the torque meter. So we use torque meters to measure how much power the engine is providing. The tail rotor. The tail rotor is primarily used to counteract that main rotor torque that we just discussed. The tail rotor can also be used to provide yaw in some designs for the helicopter. The tail rotor is also a variable pitch rotor that produces thrust in the horizontal plane. This opposes that main rotor torque. The same issues that plague a main rotor system with regards to the advancing blade producing more lift than the retreating blade. Mind you, every blade is at one point or another going to be the advancing blade and also going to be the retreating blade at another time. But the advancing half of the rotor disc, if the helicopter is in forward flight, is this. If say the blades are rotating counterclockwise, going this way, the advancing blade is any blade that moves from my 6 o'clock through my 3 o'clock to my 12 o'clock. The retreating half of the rotor disc would be that blade's movement from my 12 o'clock to 9 o'clock to 6 o'clock. The same effect happens with the helicopter. This time around, if the helicopter is in forward flight, any distance from, if the clock's 12 o'clock was right here, so anything from 3 o'clock to 12 o'clock to 9 o'clock would be considered the advancing half of the rotor disc. And anything in the reverse from that 9 o'clock position to 6 o'clock to 3 o'clock would be considered the retreating half of the rotor disc. And just like in the main rotor system, on the advancing half of the rotor disc will produce more lift and the retreating side will produce less lift. Now this is the second part where we have uneven lift production. First we talked about the distribution of lift across the rotor disc from the hub to the tip because the tip is moving at higher speeds. And now we're talking about the advancing and retreating blade. How do we resolve this issue? I think we discussed this before. This problem is termed as dissymmetry of lift. And to resolve this issue, we do something called blade flapping. So all this just to say that even tail rotors as well face the same issues and also use the same principles to compensate for that. So the blades are also flapped. A rotating helicopter has some of the characteristics of a gyroscope. In the sense that because of those rotating blades, it has a tendency to be rigid and not want to move around in space. In fact, this helps us to some extent with stability in the helicopter, but also makes it a bit difficult to maneuver. When a rotor spins in space, it develops inertial force that tends to make the rotor more rigid. It resists any external movement. Some early Bell helicopters have a weighted stabilizer bar, as seen in this picture here. And this stabilizer bar turns the rotor and acts as a gyro when rotating and not wanting to depart from its plane of rotation. The stabilizer bar. The stabilizer bar is seen here as well in this helicopter module that I have here. Usually it'll be perpendicular in a two-bladed system to the two blades. It is connected intricately to the swash plate and also provides the pitch links with the required up and down movement that is used to feather the blades. Now, because it's connected to the feathering of the blades, this can act in a self-correcting manner for the helicopter. So this allows the helicopter to be able to resist or correct for any disturbances that come externally to the helicopter. Some control problems due to overstabilization are prevented by limiting the possible angular difference between the rotor and the stabilizer bar. We also have a damper. Just because we have a stabilizer bar which is used to offset any accidental inputs by the pilot, we also have the other end where it becomes oversensitive and really prevents the helicopter from being able to be controlled. So we call this overstabilization. And to prevent that from happening, in design, a damper is installed. And this is the damper. So the damper prevents the stabilizer bar from being over effective. This brings us to another principle that has to do with a gyro, and this one is known as gyroscopic precession. Gyroscopic precession is simply the tendency of a disturbance to be delayed. When a body is spinning, if a disturbance acts at a position, the reaction is felt, or the effect is felt, approximately 90 degrees later in the direction of rotation. So if we had an object rotating in this plane, if we disturbed it here, the tendency is we'll feel the effect approximately 90 degrees later in the direction of rotation. The highest angle of attack is applied to the retreating blade at 90 degrees to the left. So if we apply it at 90 degrees to the left, the maximum up deflection of the rotor blades occurs approximately 90 degrees later at the tail. This would be quite confusing if it wasn't adjusted for or compensated for by the arrangement of the swash blades and torque links and pitch links. Because if a pilot intended to go forward and was trying to produce maximum angle of attack at the rear of the helicopter, if the helicopter blades were rotating counterclockwise, what would eventually happen is that the helicopter would end up going to the left, because the maximum lift, instead of being produced at the 6 o'clock position, would eventually be produced at the 3 o'clock position, which would cause the helicopter to roll to the left. If the rotor disc was rotating clockwise and we didn't have this compensation taking place in the swash plate assembly, what would happen is the helicopter would intend to produce maximum lift or maximum angle of attack at the 6 o'clock position, causing the helicopter to go this way, but instead what would happen is the effect would be felt approximately 90 degrees later at the 9 o'clock position, which would cause the helicopter to roll to the right. This is gyroscopic precession. The next thing I want to talk about is Coriolis effect. A helicopter rotor can be affected by Coriolis effect. Coriolis effect is also known as properly as conservation of angular momentum. It's best illustrated by a figure skater when they spin. So when the skater's arms are extended out, the rotation or spinning slows down because the skater's center of mass is further away from the axis of rotation. When the skater's arms are retracted in, the spinning rate increases because the skater's center of mass moves closer to the axis of rotation. On a helicopter, this is noticed on the advancing half of the rotor disc when blades tend to speed up. By speeding up, they would effectively produce more lift. When they produce more lift, this would cause them to produce yet more lift again, similar to what the figure skater does when their arms are closer to their body and the center of mass is closer to the axis of rotation. In a helicopter, this axis of rotation is actually right through the hub, through the vertical axis, passing through the center of the hub. And these would be the blade angles. As the blades cone upwards due to producing more lift on the advancing half of the rotor disc, they would tend to move even faster. So Coriolis effect causes the blades to accelerate. As the blades move down, its center of mass moves away from the axis of rotation. Coriolis effect causes the blades to decelerate until the blades reaches neutral. Below neutral, the blades again will once again start to accelerate again because the center of mass begins to move again closer to the axis of rotation. And this is Coriolis effect. You may be wondering, how do we compensate for Coriolis effect. We allow the helicopter, through design, to be able to lead lag without bending the blades. So blade lead lagging is used to counteract or compensate for Coriolis effect. The next phenomenon I want to talk about is ground effect. We discussed ground effect in class, and I think the example we use is that pillow effect. You may have seen birds that love to coast right above the water. Some of the downwash from their wings produces, let's call it, bonus lift. Ground effect is simply that bonus lift that is produced when the downwash is restricted by surface friction. As the helicopter operates near the ground, the rotor's downwash is not allowed to flow freely and dissipate. Instead, it's allowed to build up and bounces off the ground. This causes an additional amount of lift that is not due or not expected for a given angle of attack or blade pitch. Ground effect usually occurs less than 1 rotor diameter from the surface. So when the helicopter is closer to the ground, there will be a tendency for that downwash to be restricted and you get more lift. It acts like there's a pillow underneath the aircraft. When the helicopter is out of ground effect, blade tip vortices increases because the induced airflow is no longer restricted. A higher pitch and more power is required when you're out of ground effect. When you're in ground effect, you need a lower pitch and effectively less power to be able to have a controlled descent. So we talked about the symmetry of lift, and here we're going to talk about it some more. The advancing half of the rotor blades will produce more lift than the retreating half, and that's a summary of what the symmetry of lift is about. To counteract the symmetry of lift, blades are flapped and feathered to equalize the lift across the blade pitch. So in this helicopter that I have with me here today, or the helicopter module, it doesn't have its own flapping hinge. If it did, this blade would be able to move independent of the opposite blade. So lifting this blade would allow the blade go up, and flap down. The other type of movement that is needed to complete blade flapping is something known as feathering. So when we feather the blades, it looks something like this. We're able to feather these blades. See if I can feather the blades from here. Pardon me. Yeah, so these are the blades feathering. So this is the feathering motion where the blades change their pitch. And flapping would be movement of the blades assembly up or down relative to the center of the hub or the plane of rotation. Why is this important to know? Because in blade flapping, the advancing blade flaps up, producing more lift supported by Coriolis effect as well, and instead it reduces the feathering, so it lowers the blade pitch to reduce the amount of lift because there's too much lift being produced on the advancing half of the rotor disc compared to the retreating half. Conversely, on the retreating half of the rotor disc, the blades droop down and they need to feather to increase the pitch of the blades to produce more lift to compensate for the significantly less lift that is produced on the retreating half of the rotor disc. And this is known as blade flapping. Combine blade flapping up of the advancing blade and blade flapping down of the retreating blade to equalize lift produced across the rotor disc. A semi-rigid rotor head features a tethering hinge. A tethering hinge is one in which it kind of rocks and tilts. So if you lift one end up like a seesaw, the other will go down. One blade flaps up while the other flaps down. However, interestingly, in a fully articulated rotor system, and this is a rotor system that features lead lag hinges, so this is a vertical hinge or lead lag hinge that allows the blades to move forward or aft relative to the next blade. And this, remember, this is how we compensate for Coriolis effect. The flapping hinge is right here. It's closer to the center of the hub and allows the blade to effectively move up or down, and that's what we call blade flapping. In a fully articulated rotor system, blades can lead lag. Obviously, blades can feather, which is changing the pitch, but the blades, most importantly, are able to flap individually, distinctively, separately from the other blades. The next issue that we encounter is retreating blade stall, because during blade flapping, the retreating blade needs to seek a higher angle of attack to compensate for the lower lift on the retreating half of the rotor disc. So if the helicopter was in forward flight, when the helicopter is if the blades are rotating counterclockwise like they are here, on the retreating half we'll need to have significantly more blade angle of attack to produce enough lift. And this high angle of attack, as we know, can reach a point where it exceeds the M crit, actually the critical angle of attack, pardon me. And once we exceed that critical AOA, now we're going to fall into the problem of having a stall. So retreating blades have a tendency to stall as we try to seek higher and higher angles of attack at lower speeds. Retreating blade is a major factor that limits the forward speed of a helicopter. Most helicopters find it very difficult to fly quite as fast as other fixed-wing aircraft because that retreating blade stall that happens as we try to increase the speed of the rotor. We're going to create significantly more dissymmetry of lift, which effectively will have to be compensated by a very high angle of attack, and this causes the blades to stall. That pretty much covers what we've discussed so far, and let me see if there's anything I missed. Vortex ring state. Yes, vortex ring state is another phenomenon whereby the helicopter is going to lose most of the lift produced when it's settling too quickly, when the helicopter comes into land too quickly and does not have enough translational speed. So not enough forward speed. The helicopter will, if the helicopter descends too quickly into its own downwash, this can cause disruption of lift and can actually be quite a dangerous phase of flight. So vortex ring state is also known as settling with power, and this is a condition of power whereby we drop the main rotor into its own downwash, causing it to lose lift. During a descent, if the descent rate becomes high enough, the induced airflow at the inner portion of the disc can move upward rather than downward. And this is what happens when we have vortex ring state. So the helicopter quickly settles into its own turbulence, and that spoils the airflow over the blades. So what is autorotation? Autorotation is the method in which a helicopter is able to sustain flight after engine power is lost. It's colloquial terms, a controlled fall in which we utilize the main rotor's existing RPM to be able to produce enough lift to give a pilot a successful attempt at bringing the helicopter down to the ground. There's an auto-rotative chart, and this is what we're going to be doing for our next project, in which we'll discuss how does a pilot know if their auto-rotation is likely to be successful, what rules must they follow, what RPMs must they maintain for a given altitude to ensure that there is enough inertia in the system, there's enough torque in the system, there's enough power, there's enough lift in the main rotor hubs to sustain flight until we can have a controlled landing. So let's check this scenario out. Should a failure of the engine or drivetrain in a helicopter happen, the helicopter can perform an auto rotation to safely descend to the ground to land. If these failures occur, the rotor system will automatically be disengaged, allowing the main rotor to freewheel in its original direction of flight. The rotor continues freewheeling as the helicopter descends towards the ground. The rotor's speed is conserved during this descent and used approaching the ground to slow the rate of descent to land softly. During auto-rotation, control of the helicopter can be maintained throughout the descent, allowing for safe landing. The process of producing this lift with the rotor blades as they freely rotate, freewheeling from air that's flowing up through the rotor system is what we describe as auto-rotation. So if you recall, when we talked before, we said during powered flight, the helicopter blades allow air to be sucked down through. During auto-rotation, the opposite is true, and this airflow moves up through the rotor disc. So when these blades rotate, they will effectively form a disc. During powered flight, the direction of airflow is down through this rotor system onto the body of the helicopter. During auto-rotation, the helicopter is falling down and the air is flowing up through. And this is what we term as auto-rotation. We're using that flow of the airflow up through to generate lift from the main rotor system without the use of an engine. In other words, the way that gyrocopters operate. So during normal flight, this is the direction of airflow. During auto-rotation, it's the opposite. Because the helicopter's direction of flight is downwards, air is now flowing up through and producing lift. The lift is produced by something known as the auto-rotative force. This force keeps the rotor turning as the helicopter descends during auto-rotation. The rotor is divided into different sections for explanation when it comes to auto-rotation. The rotor can be divided into 3 regions when the helicopter is in vertical rotation or in auto-rotation. One of these areas is known as the driven region, and the driven region is the outermost region. The driven region does not provide us with significant amount of benefits. The driven region is approximately 30% of the rotor disc. So if we were to divide this blade span from the center of the hub to the blade tip into 30%, this would be the outermost 30% is what we refer to as the driven region. During auto-rotation, this section is a drag force that tends to slow the rotation of the rotor. So it doesn't provide us any advantages. In fact, it is a liability during auto-rotation. The driving region, however, is the region that covers approximately 45% but this 45% starts from the innermost 25% to about 70% of the rotor disc. During auto rotation, this section is our most crucial section, as it supplies a thrust that is needed to accelerate the rotation of the blades. This driving region is also known as the autorotative region. Keep that in mind. So we have the driven region, the driving region, which is also known as the autorotative region, which is the useful region that actually helps us produce lift. The innermost section, which goes from the center of the hub to about 25% of the rotor disc, this is known as the stall region. During auto rotation, this section operates above the stall angle of attack, which is extremely high, and this produces drag that tends to slow the rotation of the rotor blades. Something interesting does happen though. During forward flight, these sections are not exactly symmetrical, and depending on the direction of the rotation of the blades before and after the loss of engine power, the section tends to tilt in the direction of the retreating side. This means that we'll have a larger than 30%, which would be the driven region on the advancing side, and would have a smaller than 30% on the retreating side. The other regions, like the driving region, are also affected in a similar manner as the stall region. The driven region on the retreating side is reduced, and this impacts flight by producing a sort of a rolling effect on the helicopter. As we discussed during powered flight, the direction of airflow is down through, lift and drag is large, and the total aerodynamic force is well aft of the axis of rotation. So this is the location of lift and drag during powered flight. As we begin to move further, in the event of loss of power, the collective is immediately lowered. So this is one of the procedures that a pilot would learn, and I would expect you to recall, is that when we lose engine power, the first thing that happens is the main rotor is automatically disengaged from the turbine system or the engines, the power plants, to prevent counter drive. With regards to the next step for the pilot would be to lower the collective lever. The effect of lowering the collective lever helps us to maintain main rotor RPM and allows the pilot more time to aviate and to think about a possible strategy for landing the helicopter. During steady state descent, the airflow is now flowing up through the rotor disc. So this is during auto rotation. The blade angle remains unchanged, yet the angle of attack is increased. So this is where we get that advantage. Because we've lowered that collective lever, it's unfeathered the blades in such a way that the direction of flight is now facing downwards, and as such we have additional lift being produced by that flow. So remember that the angle of attack for a given airfoil is the angle between the relative wind and the chord line. So this remains true, and this is why it's very advantageous for helicopters to feature a symmetrical blade system or symmetrical airfoil. The total aerodynamic force is increased and has moved forward. As long as rate of descent and rotor RPM stays the same, the helicopter descends at a constant rate. The next phase of flight, after we must have lowered the collective lever and the pilot must have aviated and flown the airplane, which is what you're always supposed to do, is to perform a flare, auto rotation flare. To slow the rate of descent prior to touchdown, the cyclic is moved aft or rearward. This increases the total lifting force of the rotor and reduces the helicopter's rate of descent. Rotor RPM increases due to the greater volume of air acting on the rotor disc during a flare. Once we've successfully flared the helicopter and reduced its momentum falling towards the ground, the next phase would be approaching for touchdown. But before we touch down, we need to move the cyclic stick forward so that the helicopter's attitude is now restored to prevent a tail strike. Once forward speed is reduced, the cyclic is moved forward to put the helicopter in its landing attitude. The collective is added to cushion the touchdown right before the helicopter touches the ground. So right before we touch the ground, now this is the time to maximize and take advantage of all the rotor RPM that has been depleted, or what's left within the rotor system, by raising the collective. This will produce an effect of lift production, but because the overall momentum of the helicopter is still downwards, this is not going to cause the helicopter to just take off and start flying again, because remember, we've lost engine power. Instead, the result would be a cushioned and controlled soft landing. During autorotation, other than for directional control, the tail rotor produces zero or negative thrust. The tail rotor is not used to counteract main rotor torque because there is no main rotor torque, as the first thing that happened was the main rotor being disengaged. Several factors that affect autorotation. We can think about airspeed, density, altitude, weight, and rotor RPM. So density, altitude, this refers to how dense the air is relative to what altitude we would typically find that type of air. So a low density altitude is air that is typically found at lower altitudes, which is better for aerodynamic performance. The airspeed is a major factor affecting autorotation. It's the pilot's primary control of the helicopter's rate of descent. If you are at 1,000 feet and do not have any forward airspeed whatsoever, this could be troublesome, because now it means that you need to sacrifice some altitude in order to gain some forward airspeed. In autorotation, little or no airspeed will cause a high rate of descent. If we don't have sufficient forward airspeed, this could lead to a high rate of descent, which is not a desirable thing. An intermediate or average airspeed will allow for minimum descent rate. So it's important to not have excessive airspeed or have insufficient. Just having an average or intermediate airspeed is the best case scenario for producing a very low descent rate, which is a desirable feature. Airspeeds above the intermediate will cause a higher rate of descent as well. The next factor we want to discuss is density altitude. Density altitude affects autorotation. At higher density altitude, the helicopter will have a tendency to have a poor engine performance as well as aerodynamic performance. A higher density altitude will generally require slightly higher airspeed to get a successful autorotation. The next factor is gross weight, or rotor RPM. The helicopter's gross weight is an important factor in how it will perform during autorotation. The higher the weight, the lower the desired descent rate. So if you have a very heavy helicopter, you will actually be looking for a very low descent rate. A higher gross weight during descent would tend to cause the rotor to accelerate too much, possibly causing overspeed of the rotor. The collective is adjusted to increase blade angle to maintain proper RPM during descent. In fact, the collective is one of the primary ways in which we can control the RPM once we've lost engine power. We do this by increasing the blade pitch or decreasing the blade pitch to manipulate drag. If the rotor system had too much RPM, we would increase or raise the collective to change the blade pitch, increase that blade pitch, which would in turn generate more drag, which would help the blade to slow down until we match the range that we desire in our auto-rotative chart. Our stabilized rotor RPM. Conversely, if the rotor RPM was too low, we would lower the collective to reduce the amount of drag and give the helicopter blades an opportunity to maintain or increase the speed or the stabilized rotor RPM as desired. So the collective is adjusted to increase blade angle, which helps us maintain proper RPM during descent. Rotor RPM. Maintaining rotor RPM throughout auto rotation is very crucial in order to have a successful auto rotation. Once the collective is lowered fully for auto rotation, the adjustment is continuous to maintain proper rotor RPM until the airplane is safely on the ground. Rigging. There's something that we do when it comes to rigging the system in the flight controls and rigging that collective, which you can see here in the picture on your right. Most helicopter collective controls are rigged in a way that at their normal gross weight, which is expected, the collective will have to be raised slightly to keep rotor RPM during auto rotation. So it's not rigged to be put down completely, but you want to be able to raise it up just a little bit so that in the event that we need to, we are able to get a little bit of increase in speed where needed. This chart here is very important, and it shows us the area in which operation is dangerous. Height velocity chart is published in the operator's manual for each type of helicopter. You can see the height above ground in feet, and you can see the forward airspeed. And there are two areas here that are highlighted in red on this grid. The one to the left shows an area where we don't have enough altitude, and the one here shows where we don't have enough forward airspeed, or vice versa. The altitude speed chart, or also called the height velocity chart, illustrates the helicopter's auto-rotation capabilities, and this is different for every aircraft with regards to the helicopter's height above ground and its speed. In the shaded area, this is places where you should avoid operation for continuous periods of time. The one on the left is known as the dead man's curve, or the coffin corner. So in this case, you either don't have sufficient forward airspeed for the altitude that you possess. The shaded area on the left shows the areas where successful auto-rotation is not likely to be possible in the event of engine failure. So do not operate the helicopter for continuous periods of time in this area here at all. So if we take this position right here, where we have a height above ground of about 300 feet, and we have airspeed of about 20 knots. The problem with this is there isn't enough time for safe descent. The reason for this is primarily because of insufficient airspeed to enter auto rotation. So we don't have enough forward airspeed. The helicopter was likely in something of a slow flight or a hover, and this puts the occupants in danger. The shaded area on the right is also also a no operation zone. The danger of operating in this area is insufficient time for auto rotation due to close proximity to the ground. So over here, yes, you have enough airspeed. If you were anywhere in this area, operation would be safe. Continuous operation is advised. But if you are so close to the ground, even if you have sufficient airspeed, there is not enough time for you to respond. Over here, you have sufficient altitude, like over here for example, but you just don't have enough forward airspeed. So you're going to end up sacrificing a good portion of your altitude just to gain some forward airspeed. A hover at 50 feet above the ground is in this area of no operation. Insufficient airspeed and altitude is available to execute a successful auto rotation. Flight at 175 feet, so somewhere here, with a speed of 20 knots is also a place that you should avoid. The reason you're avoiding this again is because yes, you have enough altitude, but you don't have enough forward airspeed. On illustration B, you're flying at just 10 feet above the ground, even though you have good forward airspeed. Continuous operation here is not advised because you are unlikely to have a successful auto rotation. Some height velocity charts will compensate for changes in density, and these ones are quite useful. If you have a high density altitude, as you can see here, the areas where you shouldn't operate are increased. So having a low density altitude, like I mentioned before, is an advantage. This means that you have very dense air, and this dense air is good for the aerodynamic performance of your blades, and this will affect how much lift you're able to produce. If the air is less dense correlates with a higher density altitude. You have this issue here where you need to avoid operation in a larger and larger area for continuous periods of time. During auto rotation, low RPM is a dangerous condition. If it's not corrected, it will leave very little kinetic energy in the rotor for deceleration and touchdown. The mass of the rotor system contributes to the rotor RPM throughout this sequence. So let's talk about different designs. Rotor system mass along with the speed contributes, as we know, to the amount of inertia that is produced by the rotor system. So we have a high inertia rotor system versus a low inertia rotor system. So what are these exactly? During auto rotation, a high inertia rotor system freewheeling at a proper RPM will store large amounts of kinetic energy throughout the descent. What that means is there's high amount of energy, and it's likely that after you go through your phases of first disengage, push the collective down, aviate the helicopter, flare, correct, touchdown. In touchdown, you're likely to have sufficient energy in the system to get a soft, nice landing. But it's not all good. A high inertia allows the rotor RPM to be maintained and used during the flare and landing. Due to the high inertia rotor, RPM would tend to decrease slow as the stored energy is used. Now let's talk about the drawbacks of having a high inertia rotor system. The disadvantage with this system, however, is if you are careless and you presume that you have all this excess energy and you lose the energy, it's very difficult for you to regain RPM. So it's slow to deplete, but also extremely slow to regain. If the RPM is allowed to get too low during auto rotation. Regaining proper RPM is difficult and requires a higher rate of descent. Low inertia rotor system. This system tends to slow down very easily. Doesn't store tremendous amount of energy in the system. However, the advantage is it's very easy for you to gain RPM if you need to. So it loses the RPM easily, but it could easily regain it as well. The advantage here is that proper you are more likely to be able to generate lift and regain some of your rotor RPM if you lose it. The disadvantage is that it's very difficult to maintain proper RPM during auto rotation with the low inertia rotor system. In auto rotation, a low inertia rotor system will have less stored energy for deceleration and landing. It would not be advantageous to design all helicopters with high inertia rotor systems, because smaller helicopters would then be required to carry enormous weight, massive main rotors throughout their flight when it's not during auto rotation. That's why you see that some helicopters will have a much smaller, lighter weight rotor system and may have a low inertia rotor system, because it's more efficient for powered flight. In summary, we've described what auto rotation is. We've talked about what freewheeling is. So freewheeling happens when the main rotor is disengaged. We talked about auto-rotative forces. We described the main rotor disc. The outermost portion is known as the driven region, which is not very useful to us. And it's about the outermost 30% of the rotor disc. From about 25% to about 70% of the rotor disc, if you were to divide it up, would be the driving region. And what did we say another name for the driving region is? We said it's known as the autorotative region. This is the region that produces a lot of the autorotative force. The innermost 25% is known as the stall region, and this region as well is a liability. And that summarizes auto rotation. Ground resonance and the instability that comes from this. We'll also be touching on vertical and lateral vibrations, how these vibrations are propagated, and how that translates into ground resonance effect, what we can do to recover from ground resonance effect, etc. Ground resonance and stability. What is ground resonance? We're going to talk about what factors contribute to ground resonance, describe ground resonance and stability with regards to different helicopter types, and let's get started. So ground resonance, vibrations are not uncommon for helicopters because we have large rotating bodies. Vibrations can occur on the ground in fully articulated rotor heads. In a fully articulated rotor head system where we have lead and lagging happening, sometimes you can have the blades bunching up together. This means that say blade number 1 is leading while blade number 2 is lagging. This will cause uneven distribution of the blades around the main rotor disc, and this can lead to a vibration which, if not properly dampened while the helicopter is in contact with a surface, those vibrations can be amplified over time each cycle until it causes a violent shaking of the helicopter. So ground resonance, this is a self-generated out of balance condition in the rotor, often associated with landing, but can also occur during takeoff or ground run-up. The problem is the result of blades position around the lead lag hinges of the rotor head. So if this blade was to lead and this blade was to lag, you can see that the distance between the two blades would be too small and will cause an imbalance, similar to what you would find in your washing machine. On the ground, the blades can become out of phase with one another. This is the term that we use, which is bunch up. Each in abnormal positions about their vertical hinges. Another name for the vertical hinge is the drag hinge or the lead lag hinges. So when these blades lead and lag, if they bunch up together, this can cause uneven distribution of the center of mass. So this is what it looks like, this image on your left here. One blade leads while the adjacent blade lags, causing an unbalanced centrifugal force. And we say that this is known as blade bunching. This moves the center of mass away from the axis of rotation and causes a wobble in the system. Out of balance condition can escalate quickly into circular gyrations that eventually lead to structural damage, and the damage can be quite devastating. Prevention of ground resonance. Helicopters with fully articulated rotor systems are equipped with provisions to help counteract ground resonance effect. One of these are the lead lag dampers. They slow or dampen the fore and aft movement of the blades about the vertical hinge. So this is the damper right here. So the damper is attached to the aft portion or the trailing edge of the root of the blade, and you can see that the lead lag hinge or drag hinge or vertical hinge, whatever terminology suits you better, is what allows that blade to move forward. The dampener basically prevents excessive movement by allowing a fluid to flow in a metered way through a small orifice within that container. Counteracting ground resonance effect. Well, we have landing gear shock struts that are also installed to dampen any vibration caused by ground resonance. And this is a shock strut that is found on most helicopters. Now, when you have ground resonance effect or post having that, one of the things that you would inspect is the integrity of this shock strut, because typically most vibrations like that should be absorbed or dampened by it. If it's not absorbed and we get into ground resonance effect, this could be an indication that this system is not functioning as required, probably weakened or damaged, and may need to be repaired or replaced. So these are your landing gear shock struts. Counteracting ground resonance. Vibrations dampened by both shock struts and helicopters equipped with wheel landing gear systems will also be able to absorb some of that. Should ground resonance occur, however, the way that we recover from this is quite simple and effective. You raise the collective and apply power. Once again, you raise the collective and apply power. This breaks the cycle of vibrations bouncing from the top of the helicopter, bouncing off to the bottom and accumulating over time. So the way that we recover is you raise the collective. This will change the pitch of all the blades, increasing the pitch, creating lift, essentially helping you break contact with the ground and terminate this effect. This now brings us to helicopter stability. How do we ensure that a helicopter is properly stabilized? What do we do if we find that the helicopter is not performing in its stability? So this brings us to positive static stability. Positive static stability, as illustrated here, is the tendency of an object, not just a helicopter, to return to its original position after it's been disturbed. So if we have a ball that's in a valley, if we disturb that ball, the tendency is the ball will eventually find its place of, find its lowest point and return to stability. And this is known as positive static stability. If we have a ball that's on top of a hill and we disturb that ball, the ball is not likely to return back to its original position, and we name this as negative static stability. In terms of dynamic stability, the tendency or the ability of a helicopter in this case to return to its original position after a series of reducing oscillations is what we term as positive dynamic stability. So if your helicopter was disturbed by a gust of wind that causes it to yaw to the left, if the helicopter has good directional dynamic stability, it will correct by itself through a series of reducing oscillations until it's finally returned to its original position without external help from the pilot. So these are the oscillations, and if the oscillations reduce in amplitude over time until it comes back to its original neutral position, we call this positive dynamic stability. Neutral dynamic stability, the system will attempt to correct, but will be unsuccessful in doing this. The oscillations neither increase nor decrease, they remain the same over time until the pilot intervenes. Negative dynamic stability refers to the increasing oscillation over time when an object is disturbed. So if the helicopter is disturbed in the yaw axis or the vertical axis, the tendency for that to grow over time and get worse and will need immediate intervention by the pilot is what we term as negative dynamic stability. A helicopter is usually considered statically stable and dynamically unstable if the controls remain in a fixed axis. Tilting the helicopter's rotor in the direction of flight causes dynamic instability. There are three basic items that contribute to this dynamic instability of the helicopter. And as the fuselage changes its pitch, the rotor disc will follow the fuselage. This causes the rotor disc to tilt in the direction of disturbance. A change in the helicopter's speed will also cause the rotor to tilt. Increasing the helicopter's speed causes rotor to tilt up, and decreasing the speed causes the rotor to tilt downwards. Because the helicopter's center of gravity is below the rotor, a change in this rotor speed will cause the helicopter's CG to change the pitch of the fuselage, and this changes the pitch of the rotor. We have different stability compensation systems. One of them we talked about was a stabilizer bar. A stabilizer bar uses a gyroscopic principle. Because it's rotating, it wants to remain in its plane of rotation as it rotates faster, and this helps us to solve some of those problems. The stabilizer bar wants to remain in its plane of rotation. It stabilizes control inputs by the pilot, and it also changes and acts like a self-correct mechanism. Modern rotor designs, however, have eliminated the need for stabilizer bar. The Healer 12E has a unique control system that adds stability to the rotor, and this features a stabilizer bar that looks like a little pedal, and this is used to actually induce a change in the helicopter. The two control paddles are fitted to the rotor 90 degrees to the rotor blades. These paddles serve as cyclic control to tilt the rotor in the desired position from the input. So we have several designs, and we're not going to get into them too in depth just yet. An offset hinge, though, is found on a fully articulated rotor system, and this is very important. The offset hinge, this helicopter I'm going to show you now is not a fully articulated rotor system, but the offset hinge refers to the position, the distance between where the blade attaches to this blade cuff from the hub. So offset is the distance. So if there was no offset, this blade would be directly attached to the center of the hub. Now, having an offset has been discovered to increase the helicopter's dynamic stability. Offset hinges refer to the flapping hinges of the rotor. So there's an offset between here and where the blades attach, where the drag hinge is located. The offset hinge for flapping of each blade is located further outboard from the mast, allowing the flapping movement to take place in a distance away from the center of gravity, providing greater stability. The mast is the center of rotation, which we've talked about. Moving the hinge further from the center of rotation adds additional stability. So offset hinges are good. Stability in the rotor can also be achieved by installing a delta hinge. So a delta hinge is set at an angle that is different from 90 degrees to the blade hub. So it's a bit of a slanted orientation for the blade attachment, which causes the blades to actually naturally flap on their own. This allows the blade to flap and feather at the same time. So as the blades flap upwards, as we talked about in blade flapping, blades flap upward, they reduce their blade pitch. As blades flap down, they increase their blade pitch. This is done because of the presence of a delta hinge that is not perpendicular but instead slanted, and that slantedness causes that feathering to happen while the blades are flapping up and down because of the difference in lift that is produced. Because there is no twisting motion, the blade pitch angle is automatically changed as the blade flaps up and down. This is the effect of having a flapping hinge. This helps to lessen the effect of dissymmetry of lift, which we already discussed as blade flapping. The effect can be achieved by offsetting the pitch horn. The pitch horn is in line with the hinge. So we have a pitch horn that exists the same as we have in most fixed wing by the vertical stabilizer, where the rudder attaches to the vertical stab. The tail rotor, much like the main rotor, the tail rotor endures some of the same effects. We talked about the symmetry of lift, and they also feature this delta hinge or flapping hinges. So having an offset increases stability. The helicopters feature a horizontal stabilizer. Some helicopters will feature a horizontal stabilizer, and there's some characteristics that we need to focus on when it comes to the horizontal stabilizer of a helicopter. We know that the horizontal stabilizer provides good pitch stability, so this helps us with longitudinal stability of the helicopter. The stabilizer dampens the pitch movement of the fuselage. The stabilizer is movable on some helicopters to provide trim. One important thing about the horizontal stabilizer is the fact that it is inverted. The horizontal stabilizer will often be inverted, and this allows the helicopter to lower the tail in forward flight. Some helicopters will feature a horizontal stabilizer that's actually movable, and this allows them to be able to trim the helicopter. Here's why most helicopters feature an inverted or upside down airfoil as a horizontal stabilizer. We know that as the helicopter wants to move forward, the rotor will have a tendency to tilt forward, tilting the helicopter with it. To provide a more stable conventional ride for passengers, we need to lower this very high tail. So horizontal stabilizers are inverted so that they produce lift in this plane to lower the tail of the helicopter in forward flight. I repeat, horizontal stabilizer use an inverted airfoil that helps to lower the tail of the helicopter in forward flight. Some helicopters feature, modern day helicopters feature a SAS system, stability augmentation system. This helps to increase the inherent stability of the helicopter in flight and in hover. Short-term rate dampening control inputs to increase stability and smoothness. This computer basically reads the helicopter's attitude and short-term changes to help to compensate and dampen those controls. It basically dampens and trims the pilot's inputs so that the helicopter is smoother to fly. Simpler forms of stability augmentation system uses a force trim system consisting of a magnetic clutch that holds the cyclic in the last known position. More complex systems use electronic servos that position the controls. These servos react to helicopter attitude monitored by the computer. The computer provides the servos with control commands, etc. And that summarizes ground resonance and stability. Hello, welcome back. We are going to pick up from where we left off, and it's about time that we discuss. Hello, welcome back to Rotary Wing Flight Controls. Let's pick up from here. Rotary Wing Flight Controls. We have very different types of helicopter design, different concepts, some more intricate, some more complex, while others more simple. Flight controls on different types of rotorcraft, like the gyrocopter, can differ from those on conventional helicopters. That's why we want to cover them. This is a gyrocopter. The gyrocopter simply uses the principle of auto-rotation and freewheeling to propel the helicopter. This features a freewheeling rotor, an engine, and a propeller. The engine is used to create forward speed, and that is also that allows the main rotor to be able to freewheel and produce enough lift. The rotor on a gyrocopter is not driven by the engine and the transmission. The rotor is driven by the autorotative force, the same force that drives a helicopter during autorotation. Engine and propeller provide forward thrust, causing airflow up through the rotor disc. This accelerates the rotor to rotate to a speed where the rotor disc can actually produce lift. Once normal rotor rotation speed is achieved, the rotor disc produces lift, allowing the rotor to be tilted or controlled using a cyclic. Tilting the rotor forward and aft controls the pitch of the gyrocopter. Tilting the rotor laterally causes a roll. Yaw control for the gyrocopter is achieved with a conventional airplane rudder controlled by rudder pedals. The primary flight controls on a gyrocopter are the cyclic, the throttle, and the rudder pedals. Very few gyrocopters have a collective control. Gyrocopters use a direction control system. Control inputs on the cyclic tilts the rotor in the desired direction. Some systems feature a spider control system. These are used in earlier designs. This system allows both cyclic and collective controls to be used. This allows for almost a vertical jump and towering-like takeoff using the collective. On your conventional helicopter design, all cyclic and collective control inputs from the pilot are sent usually through push rods to the swash plate assembly. Swash plate assembly. So the swash plate assembly comprises of two discs, one of which is known as the lower swash plate. The one on top is known as the upper swash plate. The lower swash plate, see if we can demonstrate that here. So right here we have the bottom swash plate and the top swash plate. The bottom swash plate can move up and down, and its movement is inherited by the top swash plate, as you can see here. The bottom swash plate does everything but rotate. The swash plate assembly transfers non-rotating inputs from the pilot to the rotating part of the rotor disc. As we can see, the upper part of the rotor disc rotates with the mast, while the bottom portion does not rotate. And together, this is known as the swash plate assembly. The swash plate assembly transfers non-rotating control inputs from the collective and cyclic controls to the rotating inputs of the spinning part of the rotor system. The control rods from the collective and cyclic controls connect the stationary swash plate, by stationary we're talking about the bottom swash plate, to the upper swash plate. Collective control input causes stationary swash plate to move up and down. Raising of the collective would cause the bottom swash plate to move up, and inherently the top swash plate would move up too, changing the pitch of all the blades. So if we look again, the top swash plate inherits the motion of the bottom swash plate like this. So any movement that happens on the bottom swash plate is inherited by the top swash plate. This transfers the movement to the rotating part of the rotor disc. The cyclic linkages and control rods are rigged to compensate for gyroscopic precession. So remember, we talked about gyroscopic precession, and we said this is a tendency that a disturbance felt in the rotor system will be felt approximately 90 degrees later in the direction of rotation. The swash plate assembly is used to compensate for this, to simplify flying of the airplane for the pilots. When the main rotor is being rotated by engine power, so in powered flight, when the air is flowing down through the rotor system, torque rotates the helicopter in the opposite direction. And that's why we have tail rotors, which are there to compensate and counteract that. And tail rotor pedals move individually through linkages to vary the blade angle of the tail rotor blades, providing that tail force in whichever direction is required to counteract main rotor torque. The primary purpose of the tail rotor on the helicopter is to counteract the torque that's produced by the main rotor. This brings us to a very interesting idea that we often see, and this is the fact that we have an offset. The tail rotor does not, the vertical stabilizer, which acts like a weather vane to keep the helicopter going straight in terms of its direction, does not sit dead center on the longitudinal axis like you would imagine it would on a fixed wing airplane. Instead, the vertical stabilizer is offset slightly. And this is a primary way to alleviate the work or the loading that the tail rotor does. So what this means is it helps to compensate on its own for main rotor torque. So it alleviates some of these excessive loads that the tail rotor has to perform in order to keep the helicopter from drifting away. So offset vertical stabilizer does some of the work for the tail rotor. Horizontal stabilizer. Horizontal stabilizer provides longitudinal stability. On some helicopters they're fixed. On the ones we discussed before, they were movable to act as trim. A fixed horizontal stabilizer is found on most helicopters and helps to lower the tail in forward flight. A helicopter in flight has a tendency to fly with its nose down as the main rotor tilts forward because of the rotor force, and this increases the amount of drag and reduces the fuel efficiency of the helicopter. Fixed horizontal stabilizer is usually an inverted airfoil, as you can see here. Looks like the opposite of a wing. The reason we have this is because now you have higher velocity air on the bottom, lower velocity air on top. This will give us low pressure here, high pressure here. Things like to move from areas of high pressure to areas of low pressure. This will eventually push the tail down or create upside down lift, if you may. So helicopters feature a fixed horizontal stabilizer that is inverted. This is what we mean by inverted. The airfoil is upside down, and this helps to lower the tail of the helicopter in forward flight. During a hover, you do not need to lower the tail. The need to lower the tail only becomes realized when the helicopter tilts its nose down and the tail goes up. A non-movable shape that produces lift on the lower surface of the helicopter forward speed. Right, so this is the inverted horizontal stabilizer. Some helicopters will feature a synchronized elevator set. On some models, we have movable horizontal stabilizers that acts as elevators and are connected to the cyclic control linkage to lower the tail in forward flight. Just like fixed wing, as we get more advanced, we also have some that have a trimmable horizontal stabilizer that can actually be used just like we do in fixed wing airplanes. Early helicopter controls made use of bungees, cords, and counterweights to assist the pilot in moving the control. A ballast arm weight on the Helier 12E, like we discussed, those paddles are actually used to offset that, and so that we don't need those bungees anymore. Boosted controls. This is another very interesting topic. The helicopter uses a boosted hydraulic system to do two things. One of them is to make ease of controlling the airplane, or to improve the ease at which the blades are able to tilt. But the next one is actually to dampen the feedback vibrations that come from the rotors. So the main rotor and the tail rotor produce feedback vibration that if it's not properly dampened can be felt like a buzzing from the tail rotor on the tail rotor pedals, or some kind of a pulsation from the main rotor. So we use hydraulically boosted controls. Control boost by hydraulic assists the pilot in moving the control inputs to the rotor and absorb feedback vibration in the controls. Hydraulic controls are capable of being switched off in the event of partial failure. Mechanical backup allows for full control of the flight controls. So when we do have a failure in the system, or partial failure, we're able to switch it off, and this will now leave us only with mechanical backup. So the mechanical backup still exists. Just because we've lost a portion of our hydraulics does not mean that we've lost control of the helicopter. However, there's some consequences and some prices to be paid here in that we no longer have that dampened feedback vibration. Some helicopters will feature a mixer box. Inputs from the collective and cyclic control go through this mixer box prior to being transmitted to the swash plate. So this mixer box acts like an intermediary to basically ensure that the correct controls and not aggressive controls are being sent to the swash plate. The mixer box prevents the collective control inputs from affecting the cyclic input as they move together. We have something known as a droop compensator. As the collective lever is raised, the blade angle to the blades are increased by the same amount when we raise it collectively. This causes the rotor RPM to drop due to increased drag. So in order for the rotor RPM to remain constant, remember we have to use the collective lever throttle to do it directly, or control cam linkages that are used by a correlator, or we could use a governor. In summary, gyrocopters use the same principle that regular fixed-wing helicopters use during autorotation. The swash plate assembly features two discs, the bottom one which does not rotate but moves up and down, the top one which rotates and inherits its motion from the bottom swash plate. Hello and welcome back. We're going to cover vibration analysis. We're going to talk about vibration and how we're able to monitor that when we have excessive vibration, what kinds of vibrations those are, and what that tells us about what's happening within the helicopter's rotor system. So our objective here is to describe rotary wing flight control system, including helicopter vibrations, to achieve some understanding of the flight control system and how their interaction can be understood. High vibration levels within the helicopter when operating can lead to premature wear and possible failures of many helicopter components. Any rotating device can produce some level of vibration due to unbalanced condition. So this could either be the wheel of your car, a turbine engine, a turboprop, or a helicopter's main rotor system. They're all susceptible to those wear and tear and those imbalances, vibrations due to imbalance. The main rotor of a helicopter is also capable of producing these vibrations in both the vertical and lateral plane. So vertical plane versus lateral plane, side to side. This image here shows the vertical plane, and vertical vibration is normally typically caused by out of track condition. This out of track condition talks about when one blade is flying out of phase from the other blades. So if the tip path plane is here for blade number 1, but blade number 2 is flying at a higher blade path plane, we say that one of those blades is out of track. And for lateral vibration, this comes from out of balance condition, which simply means that we have an uneven mass distribution, weight distribution within the helicopter's main rotor system. Let's discuss this further. Vibration frequencies are normally expressed in cycles per minute. A vibration of 1 to 1 means that you have one vibration or one beat for every rotor revolution. A low frequency vibration is usually associated with the main rotor and is easiest to detect. A low frequency vibration rate is between 0 to 500 cycles per minute. Main rotor vibration may be caused by faults such as main rotor unbalance span-wise or chord-wise. So span-wise would refer to from the root to the tip, and chord-wise would refer from the leading edge of the blade to the trailing edge. Things like faulty dampers or hinges or other defective helicopter components can also lead to main rotor vibration. A mid-frequency vibration is in the range of 500 to 2000 CPM. The term mid-frequency is seldom used to describe vibration in helicopter. A faulty cooling fan or a higher frequency fault of the main rotor could cause a vibration in the mid-range frequency. For helicopters, having excessive vibration is a problem, and passengers don't enjoy flights because of it, and as such we try to avoid these vibrations at all costs. The tail rotor is also prone to generating vibrations. The tail rotor rotates at much higher RPM than the main rotor because of its sheer size. Vibrations caused by the tail rotor will usually be in higher frequency due to the high RPM of the tail rotor. The tail rotor vibration are high frequency vibrations that are usually felt in the tail rotor pedals as a buzzing or tingling feeling in the pilot's feet. High frequency vibrations can be caused by other high RPM components such as the engine or transmission, and can be felt through the airframe in stationary component as a buzz or tingling. This is how the vibration is felt. Blade tracking. So we talked about vertical vibrations and we talked about out of track. Blade tracking is a process carried out to reduce the vibration in the airframe caused by the main rotor or the tail rotor. This vertical vibration is a result of unequal lift being produced because, once again, one blade is flying at a higher tip path plane, which would mean that its center of mass for that particular position would be closer, which means it'll move faster and produce more lift. And that difference in lift between one blade or another causes vertical vibration. The vibration is felt in the vertical plane. This is the antiquated method for tracking blades. Blade tracking refers to the adjustment of the blades themselves to allow the blade tip path to fly in the same plane of rotation. So if one blade was flying in this plane of rotation and every other blade was passing through the same tip path plane, we say that the blades are in track. If one of them was sticking up or sticking lower, we say that blades are out of track. Each blade can be adjusted to fly in the same tip path plane. We have a quick way of doing that, and it's by adjusting these trims that are found in some blades. So the trim tabs can be adjusted to cause a blade to fly in a higher tip path plane or lower tip path plane so that it meets up with other blades and avoids that vertical vibration. Now this is the quick method, and this is not very efficient in the sense that usually blades will return back to their original out of track condition. Another way of doing it is actually by adjusting the length of this threaded rod that is known as the pitch links. So the pitch links feature a threaded rod that go from the swash plate assembly to the blades and help the blades feather. So in order to do this, you must first cut this safety lock wire, and now you can either lengthen the rod or shorten the rod as required to adjust the tip path plane of a given blade. Methods of blade tracking include the stick method, which we just showed, where you have a pole, a handle, and someone holding it. And we have other methods that use lasers or light reflected methods to show in track or out of track. Modern blade tracking is accomplished by pre-tracking method and electronic strobe method, where you have an electronic strobe generator that is pointed at the blade tip and is able to analyze whether a blade is in track or out of track. Tail rotors are also dynamically balanced by blade tracking. Many methods used are similar to those used for the main rotor, essentially to make sure that the tip path plane is the same and one blade is not producing excessive lift. That summarizes vertical vibrations. Now let's move on to lateral vibrations. A lateral vibration comes as a result of unequal distribution of mass in the main rotor disc. The vibration is felt in the lateral plane. Lateral vibrations can be caused by numerous problems, including improper manufacturing. Assembly is one way where we as AMEs fall short, and sometimes that can lead to vibrations. Lateral vibration can also be caused by improper blade track, but we say that the primary reason why we see lateral vibration is from out of mass or uneven mass distribution or out of balance condition. Additional weights can be added to the blade in the main spar area, and this is how we're able to adjust that uneven mass distribution and make it more even. This prevents lateral vibration caused by unbalanced rotor during rotor blade rotation. Weights are used to balance the blades like you would on high engine vibrations on like your turbine engine aircraft. Rotor head balance. The main rotor head on some helicopter models is statically balanced separately from the blades. The entire system is also then balanced afterwards. Rotor static balance. The rotor assembly is statically balanced both clockwise, both chordwise and spanwise, Chordwise balance is in the direction of the chord from leading edge to trailing edge. Spanwise balance is in direction of the span from the hub, which is the blade root, to the blade tip. A balanced rotor continuously seeks a level position by itself. Balance weights are added or subtracted to the rotor to achieve chordwise balance. Blade balance weights can be added to the helicopter blades to achieve this. With regards to span-wise rotor balance, this can be achieved also by adding additional weight in strategic locations in the hollow parts of the blade retention bolts. Just like we can balance main rotors, we can also balance our tail rotors in terms of mass distribution. And that concludes vibrations for helicopters. Summary: main rotors and tail rotors are all susceptible to vibrations because they rotate. We have two main types of vibrations: vertical vibrations, which come from uneven lift distribution. That uneven lift is caused by one blade flying at a different tip path plane than another blade. The next type of vibration is a lateral vibration, as we said, and this comes from an unbalance in terms of mass distribution and problem, and this can be fixed by adding additional weights either in those retention bolts that we find at the vertical hinge, or by actually adding weights through the spar of the blades.